In this video, we will study the inclined plane. Our inclined plane is currently going to be frictionless. It's going to be a plane that makes an angle theta with the horizontal. And what we have is a block of mass m sitting on this plane. Okay, so if we let go of this block, we understand because it's frictionless, it's going to start sliding down the incline. Okay, our goal is in this video, is basically figure out what to do with all the forces that are acting on it. Okay, and once we understand this video, or once we understand what you need to do with blocks on an incline, then even with connected blocks, we will be able to solve problems that involve connected blocks. And essentially, when friction comes into our lives in a little bit, we'll be able to tackle those as well. Okay, so this video is super important. Make sure you understand all the little pieces of this video. If you do not, I'd suggest you watch it again, and then obviously I'll try to go over it in class as well, just to make sure that we're all on the same page. Okay, but this is extremely important, and it's pretty straightforward. But there are a few pitfalls, few places where people do make mistakes. So I'm going to emphasize that, and then we will hopefully everybody understands it and nobody makes any mistakes with it. Okay, so here we go. First thing I want you to do is draw the forces acting on this block. Okay, when you draw the contact force, remember what we said about the contact force. There's an important characteristic. If you don't remember, look back in your notes. It should be there. Okay, but take your time, draw the forces, and then pause the video and come back. Alright, so I'm assuming that you did that. I am going to draw the forces on this block right where the block is. Okay, so my one force we know is gravity, okay, acting straight down, and draw big. In this case, just draw big. Make sure that this picture is a large picture. Use colors if you can, and that way, things will be much clearer. Okay, so we have gravity, and then we also have the contact force in this case. Okay, now the contact force, I'm going to draw the contact force. I'm just going to do this. So we know what. Okay, so the thing that I was talking about, the contact force, is that the contact force is always perpendicular to the contact surface. Okay, so in this case, the contact force is not going to be pointing vertically upward. If you had that in your picture, that would be a mistake. Okay, the contact force is going to be perpendicular to the surface. Okay, so this is going to be Fn, the contact force. And I'm not sure if I clarified this in class. The reason we write Fn is because it represents also the normal force. Okay, and in geometry, normal means perpendicular. Okay, so we call it the normal force, the contact force. So here we have. So we have these two forces. Now we know that this block is going to slide down the incline in this case because nothing else is going on. If we had a string attached to this block that passes over a pulley and connected to some other block, there's a possibility that this block could be moving up the incline. But in this picture right now, it's moving down the incline. The important thing is that the direction of motion is parallel to the incline. Okay, so keep that in mind. Now, because the direction of motion is parallel to the incline, okay, and also because of the fact that these two forces, Fn and mg, are not just pointing along, are not directly opposite each other or perpendicular with each other, we need to do something here. Okay, and what we need to do here is, because the object is going to move up or down the incline, okay, we're going to call this the incline itself, the direction parallel to the incline, as our x direction, and the one perpendicular to it as our y direction. Okay, so we're just going to call this our x and this would be our y direction. Now, the reason we do this is because the object is going parallel to the incline. Okay, so we choose our axes based on that. So remember that. The best axis to choose is always one parallel with the acceleration and another one perpendicular to the acceleration. Make a note of that. Okay, now once we have this, now we ask the question, which force is not pointing in the direction of our x or of our y? Okay, clearly Fn is pointing along the y direction, so we just leave it alone. Mg, on the other hand, is not pointing along the y direction. Okay, mg is acting in between the x and the y axis. So what we need to do at this point is break mg into components. Okay, and writing the components of mg correctly is basically what is the key element that you need to get out of this video. Okay, so in what we have is we have a force mg and we have an axis, and we want to write the components of mg relative to this axis. Okay, in order to do this, we need to figure out the angle that mg makes with either the x or the y axis. Okay, so let's figure this out. We know that here we have a right angle triangle, like this whole thing is a right angle triangle. Okay, if this is a right angle triangle, if this angle is theta, you can all figure out what this angle is. Okay, and if you said 90 minus theta, then you are correct. Now if this angle is 90 minus theta, clearly we see that this angle here is also theta. Okay, so make sure you understand this. Okay, so look, this is 90 minus theta, so this angle is also 90 minus theta, and because the two axes are perpendicular to each other, if one of the angle is 90 minus theta, the other would be complementary of that, which would be theta. Okay, so what we have is this angle theta, which is extremely important. As soon as we have the angle theta, now we are ready to draw our components. Okay, so first this would be a component, okay, along the y direction, and then this would be the component of mg along the x direction. So let's call this guy f perpendicular to the surface, or fg perpendicular, and let's call this fg parallel to the surface. Okay, now at this point we are ready to write the components of mg. Okay, so go ahead and write the components. What do you think is fg parallel? What do you think is fg perpendicular? Right, pause the video and then come back. All right, so I'm assuming you have something. Okay, it doesn't matter if it's wrong, we'll figure this out. Now if you have or rather, no, let's go through the logic here. So if we know from writing vector components, okay, when if you look at this angle theta, okay, the common mistake that people would make is because there is an angle theta, they might end up saying that this component is mg cosine theta, and then that this component, the y component, is mg sine theta. If you did that, okay, you made a mistake. Let's see why this would not be correct. Okay, so let's use basic trigonometry here. We know that the angle theta, okay, is the angle. If we were to say finish this right angle triangle, do you see how FG perpendicular is the side adjacent the angle theta? Okay, so which ratio goes with adjacent? Okay, it's cosine theta. So FG, this component, the perpendicular component of the gravity, okay, is going to be mg times cosine theta. Okay, and then we use the same logic here. FG parallel happens to be the opposite side, okay, and then this ends up becoming mg times sine theta. Okay, make sure you understand this picture well. Okay, and then take everything. Once you get this, make sure that uh, you know how the components come out. Okay, now if you understood this picture, what I suggest you do is try out this one. Okay, so I'm gonna draw this guy some inclination theta. Okay, and put a block m here. Okay, and once again what I would like you to do is, you have mg pointing down, then you have fn pointing up, and I want you to write down the components of mg. Okay, we will choose our direction to be like so. Write down the components of mg. Write down the perpendicular component of the force of gravity, and also the parallel component of the force of gravity. So go ahead, do this, pause the video, and then come back. Okay, so I'm assuming that you went through the process. I'm going to redraw my vectors, okay, the not vectors, the components of FG parallel and FG perpendicular. Now I want to point one thing out. When you draw these components, okay, remember the components are sides of a right angle triangle with MG being the hypotenuse. Okay, so you should be able to form a rectangle with mg and the two components. If the components are longer than that, then you gotta adjust the length. Okay, it doesn't have to be perfect, but it cannot be way off. Okay, so Having said that, once again, we know that this angle is theta. So this angle here, once again, would be theta, which is the angle that FG perpendicular makes with the actual vector. And therefore, our component once again would be written as mg cosine theta for the perpendicular component and mg sine theta for the parallel component. Okay. Now, in either cases, if you had to find the acceleration due to gravity, okay, what all you would do is, if you look at the direction of motion, which is along this x-axis, right, we would have mg sine theta, the only force pulling it down, and this would be equal to ma, and therefore a would be equal to g times sine theta. Okay, let's explore this a little bit. If the angle of inclination is decreased, okay, you see sine theta would decrease. And when the angle of inclination is 0 degrees, which is when the object is when the plane is horizontal, sine of 0 would end up being 0. Use your calculator and check that out. And so this equation tells us that when it is when the incline is horizontal, when the angle theta is 0, there is no acceleration. Okay. Now the other extreme would be when the angle is 90 degrees, and when it is 90 degrees, sine theta simply becomes 1, and at that point the object is in free fall. Okay, so it gives us the correct values for the two extremes, one for the horizontal and one for the vertical. Okay, the last thing here is also to calculate Fn. Okay, so the normal force you see is simply going to be equal to mg times cosine theta. Okay, as there are no other forces acting on the system. Remember that the only reason Fn is equal to mg cosine theta is because nothing else is going on. This is not a generic answer. Okay, similarly, a equals g sine theta is not a generic answer. Okay, depending on the problem, that answer will change. So we will do one more problem based on this, and then that'll be the last video as far as the blog goes. All right, so hopefully this all makes sense. In the next video, we'll tackle a problem with blocks and inclines and all that, and then hopefully everything should make sense. All right, that's it for this one.